what exactly are rotations? And how can we use the tools of linear algebra and matrices to describe what rotations are in 2 dimensions, 3 dimensions, or even in a higher number of dimensions? Rotations come up in such a large number of applications that it's nice to have a really strong understanding of them. And indeed, this video is just one on my entire playlist on linear algebra. The link to that is down in the description. Let's begin by describing exactly what a rotation actually is. I mean, we all have intuition for what rotations are. For example, a globe spinning on an axis has an axis of rotation. But what exactly does it mean to be a rotation? Well, I'm going to describe a rotation as having 3 basic geometric properties. Firstly, a rotation shouldn't stretch lengths. If I start with vectors of given lengths, after the rotation is done, they are all still the same length. And this requirement blocks transformations like this one. This is a spiral transformation where it looks like it's rotating, but it's also stretching the vectors as it rotates. Secondly, rotation should keep the angles between vectors fixed. Like if these 2 vectors start with a 90-degree angle between them, after rotating, the result should also have a 90-degree angle between them. And that might initially seem like enough, but consider this transformation. This reflects over the y-axis, and it's definitely not a rotation visually, but it does keep the lengths of the vectors fixed, and it keeps the angles between them fixed. It started at 90 degrees and it ended at 90 degrees. The problem is that it changed the orientation of the vectors. At the beginning, I started with the pink vector, and then I moved counterclockwise to get to the blue vector. But with this reflection, now it's the other way around. Moving counterclockwise, I would start with the blue vector and then go to the pink vector. The orientation of those vectors has switched. And so these are my 3 different rules. I will say that these describe a rotation. They fix the lengths, they fix the angles, and they fix the orientation. Now what I want to do is take those 3 geometric properties of rotations and translate them into properties of matrices and the language of linear algebra. But how do I even know that that's appropriate? I mean, rotations might not seem like they have much to do with lines, but consider this visualization. If I consider a whole bunch of lines through the origin and I rotate them around, all those lines through the origin just become other lines. So indeed, the subject of linear algebra is going to be very appropriate here. And to be more precise, in linear algebra, our definition of something called a linear transformation has 2 properties. First of all, if you transform the sum of 2 vectors, that's just the same thing as taking the sum of the transformation of the 2 vectors. So in this language, the transformation of u plus v is the transformation of u plus the transformation of v. And then the same is true for scalar multiplication. You can stretch a vector by a length k and then transform it, or you can transform it first and then stretch it by a vector k. If you have those 2 properties, you have a linear transformation, you're in the field of linear algebra, and matrices are going to be a great way to explain your phenomenon. So are these true for rotations? Indeed, to define the sum of 2 vectors visually, we form this parallelogram where you take a copy of the first vector, a copy of the second vector, and then the far point of the parallelogram is the sum u plus v. But this parallelogram that describes geometrically how to add vectors, well, under a rotation, all of these lengths are fixed, all of these angles are going to be fixed. And given that's our definition of rotation, it means that when you rotate this around, you get the same picture. That is, you can either rotate the vectors and then add them, or you can add them first and then rotate them. It's the same picture either way, and so indeed we get that first linearity property. Similarly, you can stretch a vector and then rotate, or you can rotate and then stretch. So yes, rotations are linear, and yes, we can use matrices to describe them. Before we continue, I want to take just a minute to tell you about the sponsor of today's video, which is Brilliant.org. Brilliant is a learning platform for all kinds of math and science and computer science. For instance, the other day, I wanted to learn about how neural networks actually worked, and it was just so cool. It started me off with the basics, like what exactly are neurons in this context, and I needed the basics at the beginning. But it built up the concepts layer by layer, always testing to make sure that I was understanding exactly what was going on. So by the time that we had worked up to, for instance, a shape recognizing network, it wasn't just cool magic, I actually understood why everything worked. I really appreciate with Brilliant how hands-on and interactive everything is. This is crucial for long-term learning. To try everything that Brilliant has for free, go to brilliant.org/TrevorBassett or click the link down in the description. And you can also use that link to get 20% off an annual premium subscription, which gives you unlimited daily access to everything that Brilliant has to offer. All right, back to the video. Now, the key thing to know about matrix transformations is that the values of a matrix are entirely determined by what happens to the standard basis vectors. So, for example, in 2 dimensions, the unit vector 1, 0, that's my first so-called standard basis vector, when it gets rotated counterclockwise by theta, it ends up at a point cosine of theta and sine of theta. That's just the definition of what cosine and sine are. Similarly, the other standard basis vector, which is 0, 1, well, it rotates and ends up at the point minus sine of theta, cosine of theta. So what is the matrix for a 2-dimensional rotation? You just put those 4 numbers together, and this gives our matrix representation for a rotation. Let's go up a dimension. Similarly, we can determine the values of the rotation matrix by what happens to the standard basis vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. For instance, this rotation in the xy plane leaves the z-axis fixed. And so it has a matrix that looks, well, very similar to the 2-dimensional rotation in the xy plane that happens in the upper left corner of the matrix. But then at the bottom right, you just have a 1 that corresponds to the fact that everything in the z component is left exactly fixed. In contrast, this rotation in the xz plane looks like a 2D rotation matrix in the z and x variables, but it leaves the y-axis fixed. That's why I put a 1 in the middle. Let's introduce some notation. For the standard basis vectors 1, 0, and 0, 1, I'll give them the names E1 and E2, maybe all the way down to En if I'm in a higher number of dimensions. So if I rotate those 2 vectors, I get the rotation of E1, the rotation of E2, and so forth. And the way I'm going to put this into the matrix precisely is a matrix that I will call R, whose columns are the rotations of the first vector all the way down to the rotations of the last vector. That's how I came up with those matrices previously. But now I want to talk about the properties of this matrix R, like what kind of things do we know is true in general. And the first thing to note is that the E1 and the E2 started orthogonal, 90 degrees between them. But because rotations preserve angles, that was one of our defining properties, the R of the E1 and the R of the E2 are also 90 degrees. Which is to say that in this matrix, every single one of those columns is orthogonal. And then similarly, we know that rotations preserve length. So if the standard basis vectors E1, E2, and so on are all length 1, the columns are all length 1 as well. So all of these columns in the matrix are orthogonal to each other and length 1. You put those 2 together, sometimes we'll either call this an orthogonal matrix or sometimes we'll call it an orthonormal matrix, depending on where you are in the literature. And I can actually describe these properties in a bit of a different way. So you might remember from linear algebra, we have this idea of a dot product. A dot product is this particular way to take 2 different vectors and multiply them together. And if you've been in my linear algebra playlist for a while, you'll know that this is intimately related with the concept of angle. But right now, I just want to show you a different notation for it. Instead of introducing a dot product as a separate notation, you could instead imagine I take one vector written not as a column but as a row, and then the other one written as a column, and just do the multiplication between those 2 matrices. It's the exact same thing. So another way to describe this is that the dot product between 2 vectors u and v can just be written as the matrix multiplication of the transpose. That's what happens when you flip columns and rows. You get something called the transpose of u and v. And then with that little bit of notation, I can actually jump from just vectors all the way to matrices. So imagine I take the matrix R transpose, so every column becomes a row and vice versa. Multiply it by R. It's going to be some matrix that I'll call R transpose times R. But what is it? Well, check out this. The way I multiply matrices is you take a row of the first matrix, say the ith row, you take a column of the second matrix, say the jth column, and then you're going to do, well, either the dot product or the multiplication of this particular row and this particular column. But either way, what you're going to get to is the ith jth location of the product of these 2 matrices. But what could this be? I mean, remember, our matrix are all orthonormal ones. So that means if you take any 2 columns, even if one of the columns gets transposed and becomes a row, but that the 2 columns are going to be orthogonal, which means that this is always going to be 0 unless it's the same column, unless the I is equal to j. And in that case, because it's of length 1, you're just going to get the value of 1. And so this is what we have. You get the identity matrix. When I is equal to j, you get the value of 1. That's just the dot product with itself. And everywhere else, the orthogonality means it's zeros everywhere. This gives you the identity matrix. Okay, so what have we got? We've got this lovely property, and it says that if you're going to be a rotation, you must have this property that the transpose times the original matrix is equal to the identity. We've cast that geometric properties of fixing length and fixing angles between vectors into an algebraic property of matrices. But while this is a necessary condition, it's actually not sufficient to guarantee that you have a rotation. There's one more issue. And now I'm going to introduce the idea of determinants. Let me suppose I take that equation, r transpose r is equal to I, and take the determinant of both sides. What happens? Well, you might have to remember some rules of determinants. It's okay if you forget them. The first is that the determinant of a product is the product of the determinant, so I will spread it out this way. This is the determinant of r transpose times the determinant of r. The second thing you might remember about determinants is that the determinant of the transpose is just the same thing as the determinant of the original matrix. That doesn't change anything. So really what I've got here is that a determinant squared is 1, which is the same thing as saying the determinant of r is plus or minus 1. Starting with those two properties of fixing length and fixing angle gets us eventually to this determinant being plus or minus 1. But which is it? Is it both? Is it one? Or is it the other? Well, determinants have an actual specific meaning geometrically, so let's return to that. In 2 dimensions, if I've got the 2 standard basic vectors e1 and e2, then this defines a square. And as it transforms, that square goes into some other parallelogram. If it's a rotation matrix, it's going to be some other square somewhere else. And what the determinant does is it's a measure of how much the area of that parallelogram changes under the transformation. But for rotation matrices that don't change the angle between the vectors or the length of vectors, the area is going to be the same thing, 1, but determinant doesn't measure just the area. It's called the signed area. It's exactly that third property that we needed for rotations. If it preserves the orientation, the determinant is 1. And if it reverses the orientation, like in, for example, a reflection matrix, the determinant is minus 1. So the third geometric property of rotations, that they preserve orientations, leads us to our second algebraic property. The determinant of our matrix has to be 1. And now it's if and only if. A matrix is a rotation matrix precisely when these two properties are true, that the rotation matrix transpose times r is equal to the identity and the determinant of r is equal to 1. You have that, you've got a rotation matrix, and vice versa. Now, these algebraic ways of describing what rotations are in the concept of linear algebra is really helpful, for example, with this question of, if I do one rotation and then another rotation, is the composition a rotation? For instance, if I first rotate around the z-axis and then I rotate around the x-axis, if I were to play both of those animations at once, what we actually get is another rotation, just one on a non-coordinate axis of rotation. So the question is this always the case that composition of rotations gives you another rotation? And it turns out, yes, indeed, a composition of transformations in linear algebra is represented by the product of matrices. Let's assume that A and B are rotation matrices, and we'll construct the transpose of the product times the product. And then we just use rules of transpose. So the first of all is that the product transpose, you flip the order and take the transpose of both, B transpose, A transpose. And then A transpose A, we know A is a rotation matrix, and so that's just the identity. We can simplify that out to just B transpose B. B transpose B, B is also a rotation matrix. That's also equal to the identity. So yes, the product satisfies that property as well. We also need to take the determinant and see what we get. Okay, again, a determinant of a product is the product of the determinants. Each of those is going to be 1. So yeah, the determinant of the product is 1 as well. We have both properties that we need satisfied, and indeed composition of rotations are rotations. Notice that when you take a combination of two rotations, we had already seen the resulting rotation can have a weird axis of rotation. So now our question is this. If you have a 3-dimensional rotation matrix, how do you figure out what the axis of rotation actually is and what the angle is rotating around that axis? To answer this, I'm going to lead you into the direction of something called eigenvalues and eigenvectors. Suppose V is the axis of rotation, the axis to which everything is rotating about it, but V itself doesn't change. So what does that mean? means if you rotate the axis of rotation, you just get the original vector, just 1 times the original vector. And you might recognize this as something called an eigenvalue eigenvector equation. An eigenvalue is a number such that multiplying the entire complicated matrix just is the same thing as multiplying by the number, and in this case the number is just 1. So on the axis of rotation, the whole crazy big rotation matrix doesn't do anything, it just leaves the vector as itself. And what's great about this is that we have a ton of tools in linear algebra to find eigenvalues and eigenvectors. Like, in general, the problem goes, I'm asking, is there a way that the matrix times the vector is just a stretching factor lambda times the vector? So a big complicated matrix turned into just a simple scalar stretching factor. And the way we solve this, okay, I'm going to subtract from both sides. I'm going to introduce an identity matrix. That doesn't do anything. It's kind of like multiplying by 1 here. And the question is there there's always a zero solution, but is there a non-zero solution? And this is completely equivalent to asking whether you can find a case where the determinant of this r minus lambda I is equal to 0. And that is just, well, it's a polynomial equation. Let me show you. If I start with this particular matrix here, now, this is a rotation matrix. How do we know? Okay, you can check that its determinant is equal to 1. You can check that the length of each of the vectors is 1, and you can check that if you take any 2 columns of this matrix, their dot product is 0, they are orthogonal. This is a rotation matrix, but for what axis and for what angle of rotation? So what you would do is you do that computation, the determinant of r minus lambda I. I will let you do that yourselves, but I'll put links down to my playlist if you want to learn how to do all these kind of computations. But nevertheless, the outcome of it is a polynomial, in this case, lambda minus 1 times lambda squared plus 1 equal to 0. And that polynomial, well, a polynomial doesn't always have real roots. It might have complex roots like 1, and then for the lambda squared plus 1 case, you just got the square root of minus 1 and negative of the square root of minus 1, so I and minus I. And this might be seeming a little bit weird because we're talking about real things rotating around. I mean, we've got complex numbers, what's going on here? But if I look at these, there's a great formula for this, by the way. You can use something called Euler's formula, and you can represent any complex number in so-called polar form. E to the I theta can be written as cosine of theta plus I sine of theta. In this case, I can rewrite what my lambdas are. I is just e to the I pi over 2 because cosine of pi over 2 is 0 and sine of pi over 2 is 1. And so we've rewritten them in this polar form, and this is great. The 1 here, that is the eigenvalue that will correspond to the axis of rotation. So if you found your eigenvalue, now you have to do the computation. You can just go and figure out what those are going to be to get your axis of rotation. But then, from the polar form of these complex numbers, what you get is that pi over 2, that is the angle of rotation. There's a little bit of work done here that if you try to find the complex eigenvectors that lead to those complex eigenvalues, that you can find an entirely real basis that spans that space. Either way, the point is the angle here is pi over 2. And so, yeah, all we have to really do is to solve the RV is equal to 1 times v to find that axis of rotation, and I've got the angle right from here. I've completed my work. And I want to go one step further just to note that in general, if you have a higher dimensional matrix, like R might be many, many dimensions, well, you do the same thing. That determinant of r minus lambda I equal to 0 equation, that's just a polynomial. Whatever it is, it's just some big polynomial in lambda. The magnitude of lambda has to equal to 1 because rotations don't stretch vectors. So all they can do is rotate them around. So you can't have a value of a stretching factor that's not 1. But they could be real or complex. So when you go and do this, in general, if you have a polynomial of degree n, you're going to get n complex roots to this. There might be some repetition. And so what you get is there's an option of it being 1. We've seen that before. That will be an axis of rotation. But you also have these pairs like an e to the I theta 1 and e to the minus I theta 1. And there might be a bunch of those pairs. If you have a 1, and sometimes you will, sometimes you won't, well, you can certainly use that to find an axis of rotation. And then for all the other ones, you get a rotation in one plane in your higher dimensional space. You get perhaps more rotations in other planes in your higher dimensional space as well. And so the final answer is how many rotations can you actually have? Well, when solving any polynomial, any complex number comes in conjugate pairs, this e to the plus I theta and e to the negative I theta. And so it's At most, like even if you have no repetitions here, it would take all the way up to n divided by 2 would be the total number of independent rotations. If you're in odd dimensions, you might get a 1 sticking out the front as well. That's why I use this symbol for the floor of n divided by 2, because going from 4 dimensions to 5 dimensions isn't enough freedom to get a third conjugate pair occurring. In truth, original motivation for making this sort of deep dive into rotations came from my previous sort of fun, more general interest video on rotations in a higher number of dimensions, where we saw this rotation of the tesseract. And one of the things that had come out of that was that in, for example, 4 dimensions, you could have rotation matrices like this one, where you've got a rotation in the xy plane and then a rotation in the zw plane. They're rotating at different speeds. But that if you jump up to 5 dimensions, well, you don't get a third rotation. You still just get 2 rotations and then maybe 1 dimension, which perhaps might be fixed. And as you increase the number of dimensions, every 2 dimensions you increase, you get another possible plane of rotation occurring. There's more to be said about quaternions and formulas to be able to compute these a little bit easier, and in general, sort of the cool shapes of our, what's called our special orthogonal group that I've been sort of alluding to behind the scenes. So this is just scratching the surface. But nevertheless, I hope you enjoyed all this sort of linear algebra perspective on rotations. Don't forget about the sponsor of our today's video, which is brilliant.org/Trevor Bassett, to get your discount or check it out for free. We'll do some more math in the next video.